Do you remember the joy of watching a pinwheel spin as a child, whether it was in your hand or twirling in the breeze on a front lawn? Behind this simple, colorful toy lies a fascinating phenomenon: the conservation of linear momentum, which plays a key role in how it spins. But here's the twist: the way you blow air towards the pinwheel's blades is crucial in determining how fast it spins or if it spins at all, because it directly affects the torque created. In our experiment, we'll be testing 3 different airflows at different radii from the center of the pinwheel. So at 0 inches, 2 inches, and 4 inches. By adjusting the radius at which the air hits the pinwheel, we'll see how that changes the rotational speed of the blades. As you can see in this video, at 0 inches, the wind would flow directly towards the pinwheel, but it won't cause any torque, and therefore it won't spin. At 2 inches, the pinwheel would spin much faster, and at 4 inches, the pinwheel should spin the fastest. To quantify these changes, we'll be using the conservation of linear momentum formula to calculate the force and, in turn, the torque produced at each radius. Torque, as we know, is directly related to the force times the radius. The more radius, the more torque, and the more torque, the faster the pinwheel will spin. For our calculations, we have assumed steady state flow and no friction. We then take a control volume of a section of the blade the airflow hits and use it in our linear momentum equation. An average airflow of 39.37 inches per second was used along with the surface area of the blade to calculate the force required to theoretically hold the blade still. This force is unaffected by radius and therefore will be used in the torque calculations for the different radii. The torque is then calculated, and we can see how the increased radii directly correlates to an increase in torque and therefore rotational speed of the pinwheel. So as you can see in these calculations, the torque for each measurement at 0 inches, 2 inches, and 4 inches are shown. At 0 inches, the torque is 0 pound-inch, and for 2 inches, it's 1.0589 pound-inch, and then for 4 inches, it's the highest. It's at 2.1179 pound-inch, which confirms our hypothesis. So whether you're remembering the childhood fun of a pinwheel or exploring the science behind it, the principles of momentum and torque are what makes it spin.